today we're doing an FRQ where there's going to end up being a damped oscillation in it. Okay, so let's read the problem together. So first of all, we have a mass on a spring. So before I'm even going to read the problem, in my head, I'm going to say to myself, okay, I have a spring. So there's three things we're always going to think about in the back of our head whenever I just see a spring. So those three things are Hooke's law, F is equal to minus kx. We know the period of a mass on a spring, T is equal to 2 pi times the square root of m over k, and we know U is equal to 1/2 kx squared. Now, I'm not saying that we're going to use these, but anytime I see a spring, I need to think of those in the back of my head, okay? And I'm just writing it down, again, even though we're not necessarily doing it on this problem. So it says experiment 1, a block of mass 0.3 kilograms is placed on a frictionless table and attached to one end of a horizontal spring of spring constant K as shown above. So the other end of the spring is attached to the wall. So anyway, the block is set into oscillatory motion by stretching the spring and releasing the block from a time at t is equal to 0. A motion detector is used to record the position of the block as it oscillates. The resulting velocity versus time graph is shown below. The positive direction for all quantities is to the right. Determine of t, including numerical values. Okay, so first of all, when we studied, this is simple harmonic motion. And we know a couple of things. We know the position as a function of time is equal to a cosine omega t plus the phase constant. Okay, now, when I look at this graph, this is very important. This is a velocity versus time graph, okay? If it starts at 0 for a position versus time or a velocity versus time graph, this means that the phase constant is 0. So now when I look at this equation, I don't have this part. So that makes it a lot easier, okay? If it didn't start at 0, then I would have a phase constant. And most of the time, they're not going to have a phase constant. Most of the time, it's going to start at 0. First of all, they're not asking me for the position versus time. They're asking me for the velocity versus time. Now, what you can do is you can take the derivative of this, or you can all maybe already have remembered what the derivative is, because we had that on our handout, that v sub t is equal to a omega sine omega t. So you have a choice. You can either have the position as a function of time and do the derivative, or you can just remember what the velocity is as a function of time already. Okay. So now for part A, again, and I should have written that here. So x sub t is equal to a cosine omega t. So we do the derivative to get the velocity. So v sub t is equal to negative a omega sine of omega t. And we're not going to go through the calculus because we already did that before. All right. But they want you to substitute in the numerical values from the constant. So that means I need to read the graph. Okay. So now here I'm going to substitute. Now here's the part where we're going to make a mistake. Most people, when you look at the graph, you're going to say, oh, this is the amplitude. The first thing we always do when we have a graph, number one, is we're going to say, what type of graph is this? Is this a position versus time graph? No. This is a velocity versus time graph. So when I'm looking at this velocity versus time graph, and I'm reading values off the graph, this value here, this is not my amplitude, is it? What is this? This is going to be V max. Okay. Now, V max is not in this equation. A is. So now I'm going to say to myself, wait a second. I know I need to get information from this graph. What can I look at the graph? So the first thing I'm going to do is the graph starts here. This is versus the time. So the time it takes to complete one cycle is called the period. So this is where it starts. If I follow the graph like this, that's the time it takes to complete one period. So now when I look down, I see the period is equal to 0.7. So what am I going to do with that? Well, what I know is, I know the period is equal to, T is equal to 0.7 seconds. I know T is equal to 2 pi over omega. So period is not in this equation, but what's in this equation? Omega. So I'm going to rearrange this equation, and I'm going to say omega is equal to 2 pi over T, which is 2 pi over 0.7. So T is equal to 8.97. But if we want, we can round that to 9. Or you can leave it to 8.97. All right. Now, here's another thing. So now I found what omega is. Oh, that was omega, right? Whoops. All right, so now this is A omega. So another thing that I know is, I know that on this graph, this has V max. I don't have the amplitude, but I know that V max is equal to A omega. So now when I do this equation, I'm going to say for part A, V sub T is equal to A omega, which is V max. Can I read that off the graph? Yes, V max is 0.16. So V sub T is going to be negative 0.16 sine, and we'll just leave it, you can do 8.97, we'll just say 9t. So that's our answer for part A. This is actually worth 4 points on the rubrics. I would say the most common mistake is that you think, because on our other homework problems, when we did the ones with the graphs, they were always it was always a position versus time graph. All right. All right, so then part B says, I think that's all we had to do for part A. It says, given the equilibrium position is that x is equal to 0, determine the equation for x versus t, including numerical values. There's two ways you can do this. You can say, hey, this is my equation for v versus t, and if I integrate that, I'll get x versus t. Okay? So that's one way to do it. So you can say that, you know, x of t is equal to the integral of v sub t dt. And you just would substitute in your values and then end up with your answer. So you would integrate whatever that was, negative 0.16 sine of 9. Remember, that's in radians per second, t. So when you do the calculus with this, x of t comes out to be 0.018 cosine of 9t. But there's actually a different way to do this. Another way to do it is, there's another equation that x max is equal to v max over omega. So 0.16 over 9, and then once you find x max ends up being, and x max would be what? The amplitude. This comes out to be well, it should come out to be the same thing, but I just want to check on the calculator. So it says 0.01778. So it comes out to be the same thing, 0.018. So then I go back to this equation here, that x is equal to cosine omega t. So I could just say x of t is equal to 0.018 cosine omega was 9t. So either way I do it, you see, I'm going to get the exact same answer. So which is the best way for you to do it? The best way for you to do it is the way that you understand it, okay? You know, either I integrate or I just use the basic form with the position, but then I would have to know how to find x max. Okay. All right. Now we're on part C. Part C says find, part C says find K. So to find K, I'm going to have to use one of my equations that has K in it. All right. So when I go back and look here, I already know the period, t is equal to 2 pi times the square root of m over k. So that's super easy. All right. So now we're going to say t is, remember, you always want to write the equation, because if you don't write the equation, you're not going to get that point on the rubrics. I would rearrange the equation to solve for it. So I would, t over 2 pi is equal to the square root of m over k. I would square both sides to get rid of the radical. And again, the algebra you can do really fast. So k is equal to m 4 pi squared over t squared. So I substituted my values, 0.3 kilograms times 4 times pi squared over 0.7 squared. And remember, you want a grader to be able to follow your work. Here's my equation. Here's substituting my values. So if I accidentally forget to press the squared button on the pi, at least I would, you know, get all of the credit except for the final answer. And that is rounded to 24 newtons per meter. All right, so let's continue. So here is the next part. So now it says experiment 2. The block and spring arrangement is now placed on a rough surface. So the rough surface means that now we're going to have friction. Okay? The block is displaced, so the spring is compressed a distance of d. So this is important because this d and this is going to be what? This distance is going to be the maximum displacement. Now, if there's friction, it's not going to always go back to d, because the friction, this is a damped oscillation. Okay? And that's the thing, realizing that this rough surface is going to cause it to be damped. So that's the key here. Now, the first thing it says is, this part is to draw the free body diagrams. Now, with the free body diagrams, again, the thing that you need to be really careful with is you need to read this. This says toward the equilibrium position, and this says away from the equilibrium position. So first of all, one of the things they might do is sometimes they might have the free body diagrams in a grid. And the reason they have them in a grid is if the forces are balanced, the arrows you're going to draw to represent the forces, if it's balanced, they would be the same size. If they're not balanced, they would not be the same size. So you have to significantly make one larger than the other. So over here, we're going to have the weight acting down, so F of G is equal to mg. And then we're going to have the normal force, but I'm going to make the arrows the same size to show that those forces are balanced. So I can do the same thing over here. And then over here, F of G is equal to mg. Now over here, what's happening here? This is my equilibrium position. So as this is oscillating back and forth, my restoring force is causing it to go back to my equilibrium position, right? So over here, where, the restoring force is acting, again, always back to this place. That's the definition of our restoring force. So in this case, my restoring force is going to go this way, and friction has to be smaller than the restoring force, because if the frictional force was greater than the restoring force, is it going to move? No. And then over here, again, you have to be very careful with your arrows. All right, so the last part is the part E. We're going to sketch a graph, okay? And it says draw a sketch of the V versus T in this case. So again, this is a velocity versus time graph, okay? And assume there is a negligible change in the period and that the positive direction is to the right. So the first thing I'm going to do is, there's not really a negligible change in the period. So as my frame of reference, I am going to first put dots as the period. So the first period, if I remember before, was 0.7. So at 0.7, I'm going to draw a dot. Then I'll do the same thing at 1.4. Now remember, when you look at the shape of a graph, if it was something normal and it wasn't damped, you have to do points as you draw the curve. So this is 0.7, so I'm going to look at where does it cross equilibrium as it's oscillating back and forth, and I'm going to use those as my frame of reference. So what I'm going to do is I'm going to say half of 0.7 is 3.5, so 1, 2, 3. So I'm going to put 3.5 here. Then I'm going to count 1, 2, 3.5. 1, 2, 3. Does everyone see what I did? Okay. Now, when I draw this graph, again, it says the period's almost the same. They said negligible. So again, we know that's 0.7. The equilibrium point is halfway. So that's why I drew 0.35 halfway in the cycle. So this will be important. So motion begins to the right, it's positive. The velocity is going to be positive. So again, the thing that we have to remember is with a damped oscillation, the velocity decreases in amplitude as the time proceeds, as it goes on. So remember, this is not a position versus time graph, it's a velocity. So I'm going to start this off like this, positive. So I'm going to start at 0, and I'm going to go positive. So let's say when I go positive here, remember with damped, it's going to decrease. So I'm going to, as I go on, I'm going to make each subsequent curve less. Does that make sense? Okay. Oops, that one should have been smaller. Okay. And when we stop this, we're going to stop this so as far as this is concerned, is where this, you're just going to make it smaller to show that it's damped. Does that make sense? And I would make sure that I definitely use these as my frame of reference, 0.7, half of that every time it goes past equilibrium. Okay, so this is the most recent one with the damped oscillation. This is from 2012. Okay, and this is an FRQ. This was FRQ number 1 actually, but it did have a damped oscillation at the end. And that's it.